recall that every square n by n matrix has associated with it a polynomial called the characteristic polynomial. The characteristic polynomial is an nth degree polynomial if the matrix is n by n. If we set the characteristic polynomial to 0, that gives us an equation called the characteristic equation. In principle, that equation can be solved to find the n eigenvalues of the matrix. Let's start with a 2 by 2 matrix and call it A, and write down its characteristic equation. Since A is 2 by 2, the characteristic equation must be a quadratic. It will start with lambda squared. It can be shown that the coefficient of lambda is minus the trace of the matrix A, and the constant term in the equation is just the determinant of A. Hence we have the characteristic equation seen here. In matrix algebra, there is a very important theorem called the Cayley-Hamilton theorem. It says that every matrix actually satisfies its own characteristic equation. In other words, we could take this equation and replace the lambda with the matrix A throughout. When we get to the det A term, we'll have to turn that into a matrix, so we'll have to write it as det A times the unit matrix. Cast in terms of A, the characteristic equation looks like this. The unit matrix it is taken for granted as being 2 by 2, so I've not written it as I2, but just as I. If we wanted, we could rearrange this equation to have A squared on one side and all the rest of the stuff on the other side. Rather like this. A squared is the trace of A times A minus the determinant of A times the 2 by 2 identity matrix. Given a matrix A, we could check that A squared does in fact conform to that equation. But I want to do something a little more than that. Let's take that equation and multiply it again by A. So multiply by A on both sides. On the left-hand side, we'll get A cubed, of course. While on the right-hand side, trace of A is just a number, but we'll have A times A is now A squared. The constant term, det of A, and now A multiplied by the unit matrix will be just A. In doing that, we've written A cubed in terms of A squared and A. However, we have an expression for A squared here. We could substitute it in. That will give us A cubed equals the trace of A times A squared, which is also the trace of A times A, minus the det of A times I. So that's substituted for the A squared, and there's still the remaining term here, so minus det of A times A. We could reorganize that by expanding the brackets and looking at the coefficient of A, and there are two coefficients of A. There's one here and also one here, so that's equal to the trace of A now squared because of the double factor here, and this other part gives minus the det of A, and that's all multiplied by A, and the remaining term is this one here, which when we multiply out the brackets gives trace times det, so minus trace of A det of A times the 2 by 2 identity matrix. In doing this, we have successfully written A cubed in terms of A and I. In principle, there's nothing to stop us doing it again. And again. And every time we see an a squared, we would replace it with the expression that I've circled in blue up here. In fact, that means that we can write a to the n as some function of the trace of a and the det of a multiplied by a, let's call that f1, plus some other function also of the trace of a and the det of a multiplied by the identity. This is a very powerful result indeed. Any power of a can be written as some combination of just a itself and the identity. In practice, finding the functions f1 and f2 could in principle be quite tedious. However, we have a smart way of doing this when we actually have a matrix and know its eigenvalues. Let me show you how it works in practice. Let's take an a, for example, to be 2, -2, -1, 3. I'm going to tell you that the eigenvalues for this a are 1 and 4. I urge you to check that by working them out yourself on paper, but this is not a screencast about eigenvalues, and we've done that elsewhere, so I'm just giving the result here. Suppose I want to find, well, let's say a to the power 4. Then we know that a to the power 4 must be some combination of a, let's call it alpha times a, and the identity, let's say beta times the identity. Now remember, this equation has come from the Cayley-Hamilton theorem and therefore has arisen from the characteristic equation. Any equation satisfied by the matrix must also be satisfied by its eigenvalues. So we could replace a with its eigenvalues. Those two eigenvalues were 1 and 4. So we could take this equation and write 1 to the power 4 equals alpha times 1 plus beta. The identity matrix is simply replaced with a number 1. And 4 to the power 4 equals alpha times 4 plus beta. That gives us alpha plus beta equals 1, and 4 alpha plus beta equals 4 to the power 4. That's 16 squared, which is 256. If we mark those equations as number 1 and 2, and we do 2 subtract 1, that gives us 3 alpha equals 255. So alpha is 255 divided by 3, which is 85. Then going back to, say, equation 1, we see that beta must be negative 84. We've found the alpha and beta. If we now go back and look at our equation for a to the 4th, we can simply substitute the alpha and beta. So that's 85a minus 84i. So a to the 4 equals 85a minus 84i. What was a? It was the matrix 2, -2, -1, 3. So that's 2, -2, -1, 3, with an 85 at the front, minus 84 times the unit matrix, which we now give its explicit form as 1001, which simplifies to 170 minus 84, negative 170, negative 85, 255 minus 84, which in turn simplifies to 86, negative 170, negative 85, 171, and that should be a to the fourth. You can in fact check. A to the fourth is a squared squared again, and a squared you can check is 6, negative 10, negative 5, 11, and that needs to be squared, and sure enough that does come out to be 86 minus 170 minus 85, 171. The method has worked. But of course it's a very powerful method. If we wanted to find a to the 139, we could do it that way, but I certainly wouldn't like to check it. What's more, this method even works if the power is not a whole number. We can find square roots of the matrix A this way, or cube roots, or negative powers. In particular, we could find the inverse of A this way. Those are all topics for other screencasts.